I'm going to spend about 30 minutes talking about, I'm going to talk about microplastics, and I'm going to talk about per and polyfluoroalkyl substances, which often get into the news most recently for the Westgate Tunnel. So, yeah, I'll do roughly 15 minutes on microplastics and then roughly 15 minutes on PFAS. So I'll start off with a bit of a background. Each year we generate a significant amount of plastic. It goes up every year actually. So in 2010, it was estimated there was 270 megatons of plastic generated, and about 5% of that plastic will enter the ocean. It's estimated the ocean now contains at least 5.5 trillion pieces of plastic debris. We now know that we have plastic ubiquitously detected throughout the global aquatic environment. Actually, they're being detected in places far from point sources. So they're actually moving into pristine locations like Antarctica and the Arctic. They pose an issue for animals that can eat them or get entangled in them. And in the scientific literature, there's over 690 reported interactions of marine wildlife with plastic debris, including over 208 cases of ingestion. And so some of the big questions that environmental scientists need to answer are, what are the source, and then what's the impact of microplastics in the environment? So you don't need to look too hard on the internet to find some pretty shocking images related to the ecological impact of plastics. So on the left-hand side here, we have a bird wrapped up in polyethylene, a shopping bag. Picture B, what we see, this is a fledgling bird. What will happen is its parents are going out, scouring the ocean for food. They're picking up plastic, thinking it's food. They come back to the nest. They give it to the baby bird, and the baby birds don't have any ability to regurgitate, and therefore they starve to death. And you've probably also heard about the ocean gyres as well. So there's big patches of garbage in the oceans throughout the world. There's 5 main gyres now where we have large concentrations due to ocean currents of plastics. So there's a variety of different types of plastics, or the scientific community has categorized them in different ways. So macroplastics are all of the big stuff, your Coke bottles, shopping bags, and all of those things. So anything, and the scientific definition became anything greater than 5 mil became a macroplastic. A couple of years ago, microplastics started getting in the news quite a lot. And it was really these things here, which are production pellet nurdles. For those of you that are lucky enough to be near the beach at the moment through this COVID period, what you can do is, when you're walking along the strand line or the high tide line and kick up that seaweed, what you'll probably find underneath that seaweed or inside that seaweed are these little things. And these are the raw ingredients of a lot of polymers, of a lot of plastic products. So you buy these nurdles and then they melt them and they make whatever they're going to make. But they also get distributed through the environment a lot. We did some work on, a lot of people are quite shocked to know this, but there's a smaller category. These in that picture is some work. We took plastic out of personal care products. So for a number of years, the large multinationals were putting polyethylene into like facial scrubs and body cleansers and things like that. And the rationale was that it basically was easier to have a uniform size, and therefore it had less gouging than, say, something like a natural product like a coconut husk. But you know, when you think about the where this will end up, it's quite an irresponsible action by those industries. And it gets a little bit worse as well. For all of our friends like to wear makeup. the filler inside of that now is a polyethylene as well, and this is a nanoplastic, and so that's anything underneath 1 micrometer. And as we get smaller and smaller in plastic, we also are getting to the level that they can cross the blood barrier to. Okay, so I'll talk to you. I do a lot of research with the water sector and, wastewater treatment plants in particular. So when this issue first came to prominence, what we have is this original model of what people thought was happening. So if I was using one of these products, which frankly, the reason I discovered it was full of polyethylene was because I had one of these in the shower. Anyway, we use that in the shower. It goes through to a wastewater treatment plant, and then it's going to be released to the environment from wastewater treatment plant through one pathway or another. So when we discovered that they were all through the oceans, people thought that what was happening was you have this polyethylene that's less dense than water, floats across the top of the wastewater treatment plant, and then will be discharged into the surface waters, surrounding waters, so the ocean or the rivers. One of the other things that's a real problem with plastics is they're actually a vector for other chemicals. So they will, the smaller you go, you'll be increasing the surface area of that plastic, and therefore you're increasing the ability for it to concentrate a range of harmful chemicals, so pesticides and industrial chemicals. And so one of the original models was actually not that the plastic itself was necessarily a problem, but it was a vector for contaminating our ecosystems, and also potentially a pathway for contaminating humans with the persistent organic pollutants that accumulated on the surface. So some of the key questions that we need in the measurement side or environmental science side is you sort of need to have these sort of abilities to know what's entering into your wastewater treatment plant system. And so when I joined RMIT, the first thing I went and bought was I went to the pharmacy and bought every single product I could find that had polyethylene listed in the ingredients. I'm quite certain that the dean at the time thought I was completely mad, because the first bill he got from me was $500 worth of cosmetics. Anyway, so this is, so part of the talk today is about the different styles of measurements as well. So what we needed to do is figure out how to quantify and measure these plastics in these samples. So this is sort of changing now. There's been a voluntary phase out of polyethylene, but in the chemical management space, there's often quite unethical behavior. And when industry is asked to self-regulate, what they might do is they'll ban a polyethylene, which is what they've done, and then they'll probably replace it with another polymer. And so, but anyway, if we look at this one here, this is a nurdle, and this is what the original field was sort of focused on. And this is the same size this is from Nivea. This is a polyethylene from Nivea on the same size, 2 mils. And what you can see is that we have hundreds, potentially thousands more fragments of polymer, which also means that we have a significantly increased surface for it to absorb chemicals. And when you start looking at this on the scale of nations, so we start getting astronomical numbers of annual emissions. So using Unilever's own data, we would estimate that 20,000 billion particles would be released annually in the US. And if you use that data in Australia, that would be 30 tons that we would be releasing into the environment if we had the same usage. Right, okay, so let's have a look at some of these things as well. So this is, and one of the biggest complicating factors for quantitative work with plastics is it's really, really difficult. And I'll try and explain to you some of these difficulties as well. So this is Clean and Clear. This is just one of them. And it had all of these different types of polymers in them. So one of the biggest issues, you might be aware that you've probably heard of microplastics, I'm sure, but you might be aware that we don't really have any regulations anywhere in the world for emission of microplastics. And one of the reasons is we don't have good, reliable measurement techniques. And so this is a really interesting example of how analytical chemistry is failing at this point, and how we can't have regulation yet because we can't have accurate and reproducible, precise measurements for plastics. And it comes down to, in some ways, we're just not really we don't have the right sort of vocab for this. So if I have a chemical, let's just say caffeine, for example, as a pollutant, the caffeine concentration in my water sample is pretty homogeneous. So it doesn't matter where I take the sample from, but the measurement I take of the caffeine will probably be quite homogeneous. If we look at all these 4 different products, the white in here is polyethylene. What you can see is that there's quite a radical difference in their shape and morphology. And this then becomes this big problem about how we bin and report this type of data. So, for example, would the water utility say, well, there can be 10 spheres of polyethylene or shards? And so, but really where the field landed on is there's going to be size categories of different polymers. Now, the other thing is about the measurement as well. All of the field measurements are based upon what they do is they drag this net behind a boat, and the net size is 333 micrometers. And so all of those environmental reports are underestimations of how much plastic is in the environment. To make our life even more complicated, there's another type of microplastics which are referred to as microfibers. So every time you wash your polar fleece, and years ago it was advertised as a positive that we were making polar fleeces from recycled Coke bottles. And, you know, my polar fleece is one of the warmest jackets I've got. But every time we wash it, we're basically releasing microplastics, microfibers into the wastewater treatment plant, and then essentially that will end up into the biosolids and then released into the environment. Okay, so if we think about measurement in the environment, typically there's 3 main processes that you would need to go for to do a measurement: sampling, extraction, and then quantitation. Now, as I said before, with microplastics, there's problems pretty much at every point of this, because if you are looking at the distribution of plastic, say at a beach, I just told you before that the place you go and find those plastics will be at the strand line. And also prevailing currents will push plastics into particular locations. So therefore, we know that we already don't have a homogeneous distribution of that pollutant on the beach. And so sampling location becomes a really critical factor. Extraction protocols. So we need to take our pollutant from our matrix, and then quantitation. So currently there are no standard methods to quantify plastics in the environment. And the method that people use, and this is actually really good for high school chemistry teachers, is that you actually can count them under a microscope. But it's not very reliable, and it's not very accurate. The way people do this is they typically, polymers are less dense than water. And what we can do is also we can increase the density of water by adding table salt, and then we filter out the supernatant, and that's where the polymer should be. And then you would then count it. For the regulators, this is reasonably problematic, because this is some images of what the real polymers might look like, and therefore it becomes difficult for us to report on these values. Typically, using a microscope will overestimate the number of plastics, because there are many natural items in an environmental sample that look similar to plastics. They have a lower threshold of 100 micrometers, the absolute lowest limit, and human bias. Interestingly enough, and I wouldn't have thought it before I started researching this field, the color blue is more vibrant to the human eye than other colors. So if it's blue, they'll have better recoveries. And the way that you really need to do to confirm your polymer is a technique called FTIR. And what you would do with FTIR is depending on the technique you have, most labs have a basic FTIR, probably not high school labs, but most university labs, where you'll get a spectrum like this and you'll compare an individual polymer to the spectrum to get an identity. The issues with this measurement technique are that the polymers will degrade with time, therefore the spectrum might not be there'll be some variations in that spectrum. This is just some annual estimates. So most of the microplastics from wastewater treatment plant actually end up in the residual solids. And you may not be aware of this, but most residual solids from sewage treatment plants are applied to agricultural land as a fertilizer. And we only really regulate these based upon a series of historical pesticides in the family of DDT, which you may have heard of. And there's no actual guidance on the levels of plastic in biosolids and how that might impact soils. And for the DIY scientists out there as well, you can tell a field that's had biosolids applied to it by looking for synthetic fibers off your polar fleece, such as this, and these are real from biosolids. And so you do see this topic in the news quite frequently, or you did. And here's just some of the selections. Actually, this left-hand one here was a high school student who used a microscope from the chemistry or the biology lab. He found plastics all through Swanbourne Beach. This is in Perth. And so it's actually an interesting case study because you can determine if plastics are present, but I think it's for an analytical chemist, it's not accurate, it's not reproducible, and it's not precise. So it is an interesting case study in trying to prove what those words actually mean. Right, and so now I'm going to talk to you about a different type of contaminant, which is called PFAS. PFAS stands for per and polyfluoroalkyl substances. And it's probably one of the most significant environmental contaminants in Australia and potentially, arguably, one of the most significant environmental contaminants in the world. For some of you, you might have seen, it's interesting when your research field gets Hollywoodized, or I'm not sure what the word would be, but anyway, Dark Waters came out recently through the lockdown period, and it was about this story here where local communities have had their drinking water contaminated and they feel there's cancer clusters that have occurred in their children. Very, very difficult to prove a chemical causes cancer. And so it's an interesting movie to watch. In Australia, we have many, many sites that have PFAS contamination. The local communities in Australia, so Williamtown, Katherine, Oakey, Sale, Shepparton, anywhere there's a defence force, most places, airports will have contaminated environments resulting from the use of a firefighting foam. Once it's released into the environment, it's very difficult to get it out. And we're going to be spending billions of dollars over the next 10 years to fix up a range of legacy, or what are now legacy contaminated sites. So I'm going to start with doing a little bit of background on PFAS, and then I'll move into some data that we've generated from our studies and plus the analytical techniques. So PFAS are synthetic fluorinated chemicals that have been incorporated into a wide variety of consumer products. It was interesting, again, 50 years these chemicals were used. Before, this is the first report where they were found prevalent in every living organism on the planet. Humans, animals, environmental media. And so it's quite a shocking revelation at that point. This led to some voluntary phase outs of this chemical. And this was started happening around in the 2000s. It didn't really gain traction in Australia until about 2013, when basically all of the drinking water contamination of Katherine and Williamtown became, people basically told, don't drink your water, which is something we wouldn't expect to be hearing in Australia. Now, this is, for me, these become sort of moral and ethical questions too, because what we observe, we find a problem with a chemical like PFAS or PFOA. These are the two most famous. And then capitalism and industry respond to making slight tweaks to the chemical structure. And this is what's happened in this space. So fluorotechnology is really important for modern society. And I think it's important that we make is because of the way they release it to the environment. So if you look through many of these, some of the items you might recognize that you would have them in is your non-stick cookware, you might have a Gore-Tex shell, Scotchgard. They're actually used in a lot of hospital equipment as well. And so there is this debate about the role of fluorotechnology in Australia. So the industry says fluorotechnology is essential technology for many aspects of modern life. And then there's this international scientific consensus statement saying we call on the international community to cooperate in limiting the production and use of PFASs and in developing safer, non-fluorinated alternatives. Okay, so the two most famous PFASs are PFOS and PFOA. And PFOS is the driving force behind much of the remediation efforts in Australia. So if you've been watching the Westgate Tunnel issue, that's this chemical that they're talking about. It's persistent. As far as we know, it'll never break down. It's mobile. It's bioaccumulative. What that means is that everyone in the audience today has this in their body, including me. It's toxic. It's a probable class 2 carcinogen. It's been listed as, both of these chemicals are listed as United Nations Stockholm Convention persistent organic pollutants. And what happened when we identified these two as being problematic is the industry reacted to create a whole family of chemicals. So what they started to do is we originally had basically two of these, PFOS, PFOA. And as the regulations started getting adopted, these R groups started to change. And every time you change one of these, you change these slightly, you get a different chemical, get a different CAS number, and you also need different measurement techniques for it as well. And so what actually happens in the real world is that this will break off, and then you'll be left with the terminal product, which is a PFOS or a PFOA-like chemical, which we know is problematic. Okay, so we've gone from 2 to over 4,700 different PFASs now. And this is a really significant challenge for analytical chemistry. So one of the things we need to determine and figure out, again, it's a similar story to the microplastics story, which is we need to understand the movement of chemicals and where they're coming from, where they're going, and where they're going to have impact. And analytical chemistry is absolutely central to that. Telling that story, because if we can't measure these chemicals, we can't answer any of those questions. So the main sources of PFAS to the environment are the industry. So we don't have any of those in Australia. The Defence Force what they used to do, and they used to do this 3 times a day out at Tullamarine Airport, they would set jet fuel on fire, and then they would use the fluorinated foams and they would put it out. And this is, every time it rains now, more PFAS is released from Tullamarine into the local creek. And so this is what it would actually look like, all this foam. But your house also has PFAS. And so many of the items in your home or the dust in your house has PFAS in it, and a range of other actually industrial chemicals. And what this also then means is because your domestic environment is acting as a conduit to PFAS through wastewater treatment plants, and then that will then discharge either as a liquid into the beach or surface water, or it will concentrate into the solids, which will then be applied to agricultural land. Landfill is also another major source of contamination in the environment too. Everything we use in modern society will end up there, and then water percolates through it and concentrates a range of pollution. And that's firefighting foams. So the Australian government has implemented some of the most stringent regulations in the world for this chemical. And if you look at this number here, I mean, this will be testing your memories of what all of these, the milli, micro, nano. So this is less than 1 nanogram per litre. That's 10 to the negative 9. It's an extraordinarily low level, and you need a mass spec to be able to do that measurement. I'm going to show you a couple of little studies to finish up on. This was a study from 2 years ago. 2 years ago, out at Footscray, there was a chemical warehouse. Well, there was a warehouse that was empty and then somehow got filled with chemicals and then somehow caught on fire. So we'll leave you to determine whether you think that sounds suspicious or not. What happened was that it stayed alight for 5 to 10 days, released a range of solvents. Chemicals included ketones, phenols, PAHs, BTEX, and PFAS was released. The fire brigade said that they actually used fluorine-free foam, which is interesting because it was phased out in 2009. This is actually a year later, the poor firefighters who went to this scene, many of them are suffering from long-term health impacts because it was essentially they were inhaling a toxic soup of chemical and partially transformed chemicals from the fire. So the runoff of the water went through what was the adjacent creek there, which was Stony Creek, and resulted in basically everything dying. That would have largely been due to the acetone and the other solvents that were being released at the time, not anything else. Okay, so I'm going to talk to you through just a couple of little PFAS studies that we've done. This is from that site there. So site 3 here is the fire. And you can see that there was a pretty clear discoloration of that water. And so when we heard about this, we were sort of a bit opportunistic. Let's go and see if PFAS was released into the water. So I told you before that, there's 4,700 of them, and it's actually quite difficult to build a method for measuring anything really at this sort of levels. We measure for 60, and that's the largest capacity for measuring all of individual PFASs in the entire country. So we're missing a massive amount of PFASs as well. But I'm going to just focus on some of these stories here, which is basically, this is PFOA, this is PFAS, but it's a whole family of them. Okay, so measurement. We do our measurement for this chemical using a technique called liquid chromatography triple quad. Okay, so the first part of this is liquid chromatography. Liquid chromatography is the physical separation of a mixture of chemicals. So you might do things like thin plate chromatography or something like that in your class, where you might put a dot of black texture on a bit of paper, put it in some water, and then you'll watch the colors separate. That's essentially the basis of chromatography. We are separating a mixture with time. Now, if you don't have a detector on the end of your chromatography on your LC, it doesn't really matter. It doesn't matter that I've separated them because I'm not seeing it, okay? So this is called, the mass spec is a detector. And so it doesn't matter what that detector is, we need something like that. Okay, so we use a process called isotope dilution. And what that means is I add in a carbon labeled version of my compound to also monitor the performance of that extraction protocol. You need to have really good QA/QCs in this type of work as well. And that includes, these are the QA/QCs that we use. Matrix spike, it's where you take a real sample, you add in a little bit of PFAS and you measure, you make sure that, say you've added in 10 nanograms, you make sure there's a difference of 10 nanograms between those two measurements. Laboratory control sample. What that is where you create a sample of a known concentration and you measure it like a sample. And you need to make sure that those numbers match. And then a blank. Blanks need to be blank, of course. We use a process called SPE, which solid phase extraction, which means that the analytes of interest are retained on a resin, and then we remove them from the water onto a resin, and then we put them into another vial in methanol. Okay, so in terms of accuracy, okay, so I mentioned before that plastics work is not accurate at all, and it's because it misses this sort of protocols. What I've got here is we have a range of chemicals on the bottom, so that's I think it's 40 or 50 there. And when you do something like this, so if you look at this number, we fortified at 5 nanograms per litre. It's an extraordinarily low amount. And then we've measured it, okay? And so the accuracy of that measurement needs to be within 70 to 130% based upon US EPA guidelines. It might sound a bit counterintuitive, but there is inherent variation in the measurement that we will get. Okay, so I'll just quickly run through some results because I'm almost out of time. This is from the Stony Creek area. What we found was, yeah, there was PFAS released from this fire. We don't know where it was released, whether it was stored in the drums in the factory, or there was actually PFAS firefighting foams used. You'll see this scale's a little bit different, right? So we've gone from a concentration. Remember I told you that regulation limit was about 1 nanogram per litre, and we're having 4,000 here. 2 months later, we did a follow-up survey and we're still about 800. So 2 months later, it's still elevated. We actually went back 2 years later and it's still elevated PFAS levels 2 years later. Let's ignore it. This is probably so one of the things we've got to figure out is where are the big emission sources for PFAS on a city level? And so this study was looking at the levels of PFAS in the Yarra River. And what we found was that the levels through the Yarra River were quite consistent, which it's concerning, but it's consistent. But we were interested in what was the impact of the rain event. And so what we're finding is that PFASs are released into the water through stormwater. So the urban environment and the runoff from the urban environment is actually providing more PFAS to the river. And if you do a back of the envelope calculation, is that the Yarra River will discharge approximately 75 kilograms of PFAS into Port Phillip Bay, which is a significantly more greater amount than the wastewater treatment plants. And with that, I will thank you for your attention, and I'm happy to take any questions you may have.
Well, thanks very much, Brad. That's really interesting. And the first thing I'm thinking about is all the seafood that is harvested from Port Phillip Bay, and you know, that I eat, and I don't really want to think about what's in that. What I'd like everyone to do now is that first of all, I'm going to go through a couple of the questions that have come up in the chat. But if you do have another question for Brad, if you can just put your hand up, and then I'll come to you as soon as I can. So the first question is from Michael Maslin, and he's talking about, he's got a question about how you might do microplastic analysis at high school. Michael, do you want to turn your turn your microphone on and ask the question.
Yeah, thank you. Just asking about year 11 students doing this water analysis task and how we could actually detect those microplastics. You talked about a microscope. Is that the only way? Is there a better or a process to do it? Thanks.
Yeah, actually we started working on getting a year 11 based practical that we could push out to people. COVID sort of got in the way. Might be able to finish it up maybe over summer. Microscope would definitely be the easiest way for you to do that. So you really, and in actual fact, it really does lend itself to being a high school prac, and those kids would love it, I'm sure. You know, fill up a Coke bottle go to the local creek, fill it up, come back to the lab, filter it. You know, you might want to, you need to probably get some glass fiber filters, but that'd be totally fine. And then some tweezers, and then move it across to the microscope stage if you had one. The other way that you could do this would be, most cameras these days are extraordinarily powerful. And I'm talking about people's mobile phones. So you could probably get a couple of rulers, put a bit of paper underneath it, either side, put the microplastics on the bit of paper, take a photograph, and that way you can get some details on that as well. You won't be able to do the identity, but you'll be able to say do color and size.
It'd be hard to get an idea of the mass, wouldn't it?
Well, I don't think you'd have sensitive enough balances to do the mass with that smaller amount, but you could just do size and size and color probably. Yeah.
Yep. There's another question from James Anderson about detectors. James, do you want to also turn your microphone on and ask the question?
Yeah, so in terms of the, you mentioned the mass spec used to detect the different PFAS that are out there. Are there any other detectors that could be used? I work at a tech school, so we've got a HPLC that we use for some of our programs, but we don't obviously have a mass spec attached to it. So are there any other detectors that can pick up those chemicals?
No.
No.
Not at that
answer.
level. I assume you've got a UV or a fluorescence detector?
Yeah.
Yeah, I mean, that's pretty cool that you've got that. I would probably, if you had do you have a fluorescence detector?
I'll have to check. I know we've got UV.
Yeah.
I'm not sure if we've got fluorescence as well.
So there are other environmental contaminants that actually respond incredibly well to, say, UV and fluorescence. So I'd probably consider caffeine or bisphenol A. Nonylphenol as well. So there's other examples of environmental contaminants that would work well with the apparatus you've got, but PFAS won't. I went from sort of one extreme to the other. PFAS is like, super tough. So it's not really for, it wouldn't really work for a high school prac.
Thanks.
But the principles would work, yeah. The SPE or, yeah.
Now, Melissa, you've got your hand up. You want to ask your question too?
Sure, I'll just find my unmute button. Hi, Brad, that was really fascinating. Thanks for all of that. I guess my question is just along the same lines, about finding ways to make this real for our year 11 students and what your ideas are. You've already mentioned, I think, that you were putting together a bit of a sample prac for year 11s. Is there any, and I had the question about finding these microparticles in soil, because you were talking about them ending up, in farmlands and things. Is that also simply a matter of getting a sample and, filtering it, or is that a lot harder?
Okay, so it would be a little bit harder because you'll obviously have a bit more matrix to deal with. Best case scenario, if you can get sort of clean-ish surface water, you just need to filter it. And then what's remaining will probably be a mixture of real particles and plastics. And, in the commercial labs, they'll use hydrogen peroxide to sort of remove that interfering organic material. But I don't think you would need to do that for, say, are practical. What you could do, and what I'd probably do, and I would focus on the larger sizes. So microplastics includes from 1 micrometer, which is pretty tiny.
Yeah.
Through,
I would imagine we'd miss a whole lot of that, wouldn't we?
yeah, I would just focus on, say, 1 mil to 5 mil. They'd probably find that really exciting too. So say, for example, you focused on the beach.
Yeah.
Now then on the beach, you don't have to worry about the matrix so much. And what you do you can even do your sample processing on the beach. What we did when we did it, we took a big tub to the beach, you fill it up with seawater, you add in your sand into it, and then the plastics really should float to the top. And then you scoop them out. Mm-hmm. So that's one way you could do it. And you need to choose your locations carefully too, because say, for example, you want to go to a pristine beach, you're going to find it, like, for example, you'd be better off if you can do this experiment to do it at, say, Port Melbourne. So, because there's more pollution there and there's actually more current pushing it through to, say, the groins there too. Mm-hmm. So you want to choose your location carefully, because I'm sure the students would be quite disappointed if they were to do this and then not have any plastics found. So it's sort of weird in my research area. It was like, we get happy when we find pollution.
Indeed. And you really don't think there's not much that we could do at a year 11 practical level for the PFAS?
No. Sorry. I'm sorry if I missed the brief as well, Mick. Yeah, PFAS is probably a bit tough.
So, Brad, I've got a question. You talked about how the polyfluoro compounds are so persistent. Why is it that they're so persistent, and how do you actually remove them from a site?
Yeah, well, this is the $1 million question at the moment, Mick. Well, they're persistent because the carbon-fluorine bond is one of the most stable. It's the most stable bond that we have, and there's very few natural microorganisms that can degrade it, and so it's resistant to chemical and biological degradation. So that's one of the reasons why it's so persistent. The second question about how we remove it. So it actually takes a huge amount of work and effort to remove it from contaminated material. So if I start with drinking water, to get PFAS out of drinking water, you'll need to use granular activated carbon, GAC, and often you might have to then run reverse osmosis on that too. So it's a very involved process to get it actually out of water. To get it out of soil, there's still prototype techniques coming through, but essentially you have to wash the soil and then you'll need to treat the water. So it's a real bad legacy issue we're given to the kids as well. It's another one.
So that creek that you were looking at in Footscray, how long do you reckon it'll keep discharging PFAS into the Yarra?
Yeah, I don't know. I mean, we only just took our 2-year samples like just a few weeks ago, and they're elevated again. We're a bit surprised by that. So it could be a reasonable period.
Does anyone else have any questions? All right. Well, in that case, I'd like you all to join me very much in thanking Brad for doing this session. I'll remind all of you that this is the first session of 4 that we're going to be doing for the November lectures this year. All the others are on the same time, but they're all on Thursdays. So next week we've got workshops, and I've sent everyone emails on how to access those workshops. But thanks, Brad, very much for the session, and I'll see all of you next week.